Okay, let's start our seminar. The first exercise. Why Tor 0 is standard product? Or maybe you have some solved exercise.
I'll say what I did. I did.
Which one?
So, by the way, do we need to speak about the problems from the previous?
Yes, of course, about some problems which we did not discuss yet.
Okay, I just did simple exercise the complex Z4.
It's not contractible.
Yes, it's a side plate, but not.
Okay.
This first.
You're welcome.
Right now.
Oh, yes. No, another. Okay.
Okay.
Okay. It's not very hard, but it's an example of acyclic but not contractible chain complex.
Yes.
Or free modules, maybe. Even. Free modules over your ring.
Yes.
Z4.
Yes, but once again, trying to understand your words. Can't I say about C, not only Z4, but on ring?
Ring Z4.
But can't I make Z also?
It's true, but over Z it's not chain complex of free modules, but over Z4 it's chain complex of free modules.
Yes.
Even.
Yes.
So no, what you want? Of course, it's true over Z also. But models over Z4, models over Z is just abelian groups. Model Z4 is some additional property that it's not just over Z, it's over Z4. Not all abelian groups are models of Z4, only of which contains of 4 torsion. Yes.
Yes, of course.
So Z4 is a little bit more particular statement.
Yes. Okay. So
More concurrent, как-то more accurate. Yes.
So we can assume like this, and obviously English of each. This is 2m. Yes, and obviously this is 0.
And this is kernel of T also.
So
It's 2 torsion.
Yes, and of course the kernel is also everything goes to 0. And this is also 0.
So our homologies are 0, so chain complex are cyclic, or exact sequence it's the same. Okay, but
this is
yes, but we claim that the chain complex is not grammatically equivalent to 0 complex.
Yes. So assume the contradiction with this symbol I just assume the contradiction. Предположим противное.
In Russian, okay.
Yes. Assume it is homotopic to 0. What does it mean? It means that there exists, just by definition, the maps. Yes.
Yes, but these maps, no, they are unique, so yes. They are only unique map from 0 or to 0, yes.
Yes, of course. Such that this is yes.
It is 0 map, yes.
Yes, because it's factors to 0.
Yes.
So this is 0, and we need this to be homotopic to
ID. No, also we need that the opposite composition is grammatic, but opposite composition is identity upon 0 itself. Yes. So yes, yes, you're right.
So
Yes.
this is
That's always true. This is 0 or identity on 0. Yes.
It's 0. Yes.
It's identity on 0. So yes, this is true always, and we need to check that there is no homotopy here. Yes.
So this is obvious. And since we need to check the 0 is homotopic to identity. So if it's homotopic to identity, then there must exist chain map with the such properties. ID of C. But assume we take its value on another. And this means that this is multiplication by 2 and this is just a set of 1 is 1. Because it's homomorphism.
No. It's homomorphism of abelian groups. It's yes, it's not of rings. It's image of 1. It's any element of your abelian group. It's image of 0 is 0, so it's abelian group.
You are right. Okay, okay, let's.
Yes, but it's not important here. Yes.
Look at it.
But it's homomorphism of abelian group, so yes. So we have 2 here, and we can.
This is impossible.
Yes.
Because we obtained the 2.
No, it's some element of Z4. It's not true that in Z4 1 is it's divided by 2. Yes.
That's kind of contradiction.
Yes. Okay. Okay. Yes. Так, okay. Very well. Okay, you're right. Okay. One exercise вдогонку. Okay, yes. For example, if you consider chain complex, if chain complex of 3 abelian groups, then it's true. Then it's acyclic. If and only if it's contractible.
Yes.
It's exercise. Okay.
I think I proved this for.
For vector spaces.
Vectors, but this is the same argument.
Oh, okay. Then okay, you can say yes. For vector spaces, it's
I
false trace.
prove for vector space. It doesn't matter. I mean, there is the same. Argument.
Okay. Yes. No. Let's see what you use. No, yeah, it is true. But for example, for vector space, it's also true that whole chain complex is quasi-isomorphic and homotopy equivalent to chain complex of homologies and 0 differentials. This is not true for abelian groups.
Yeah,
for free.
You're right. We will see.
But this is true. Yes.
Yeah. Okay. You're right. I just I forgot what I did. I proved it just by this lemma that you asked. So I need to prove that if this is chain complex of vector space. Vector space. Then it is true that star is homotopic to.
Yes. No, this is not true for abelian groups. I think yes. So no, yes, it's for. And from this you can conclude that if it's acyclic. Yes. Okay. Yes. Yes.
This is lemma.
Yes. Okay.
And proof.
This is only for vector spaces. Okay. So now we have vector spaces, and you need to check that this is true for abelian groups, free abelian groups.
Yeah, so for vector spaces it is it goes like this. So we have Cn, and obviously this is isomorphic to each n. Not each n, but I take plus some complement, because this is vector. I can always take a complement to the basis.
Zn is kernel of differential.
Yes, it's kernel.
Now then, complement is kind of it's isomorphic to image of previous. Yes.
Yes.
So it's then it's standard. It's standard notation. So it's Z, and then its standard notation is boundaries. Okay. Cycles and boundaries. Okay. It's image of previous one. Okay. No, it's image of the next one, yes, of this one, yes, yes, yes. No, because the homomorphism modulo kernel is image.
Of course, yeah.
Maybe it's, but it lies in C n minus 1, then so its boundaries n minus 1 dimensional matters, okay. Something like this, okay. It's just standard notation.
Can we stick to my
No, okay, but
because for B I have another letter.
Okay. But standard notation is Z for cycles, B for boundaries, and H for homologies.
And this is obviously isomorphic to, so here I use B.
But it's the same thing, yes, you're right, because in kernel we have homologies and boundaries of the previous domain. Oh, hello. Barbahan.
Sorry for being late.
Huh?
Sorry for being late.
Yes, sorry, okay. Bonjour. We already did exercise that chain complex of Z4, where differential is multiplication by 2 is acyclic but not contractible. And this is another exercise that for chain complex of vector spaces, this cannot be happen because because your chain complex is homotopy equivalent to homologies, and so if it's 0, then it's homotopy equivalent to 0. So if it's acyclic, then it's contractible. And here, the start of Yes. No, it's the same thing, yes, because this is image of dn and this is image of the previous one. It's the image of dn plus 1. So it's the same thing.
I understand.
So it's bn and all bn plus 1, okay. Oh, yes. And this is not true for abelian groups because this homology is maybe it's not free.
Yeah.
So it cannot be direct summand of free abelian group, yes. This is true. This is not true for abelian groups. Okay.
Of course, it can has
Yes.
Yes. So now introduce the maps. From which I introduce map. This is just this goes like this. So I identify Cn with this because this is an isomorphism.
Yes, you have inclusion, and this is chain map. No, because your differential is 0 on this part. Your differential of C1 is 0 on this part, and something on this part. Yes, it's D0 here. Yes.
So this is
in particular, it's 0 on homologies, so you have inclusion of homologies with 0 differential to your chain complex with your differential. Its inclusion is chain map. Okay, yes.
Yes. This is because this is you.
Yes.
This is obviously.
No, composition with inclusion is just a restriction on homologies. It's 0, yes, because it's part of kernel of T.
Very finish.
Okay. And you claim that this inclusion is quasi-isomorphism. This map is isomorphism of homology.
We have a chain complex and we're trying to the lemma is a
No, it's not lemma, it's kind of exercise. It's exercise which so it's new exercise. New exercise is that this is true that for chain complex of free abelian groups, if it's acyclic, then it's contractible. It's homotopy equivalent to 0. If you have chain complex of free abelian groups, then if it's acyclic, it has 0 homologies. Then it's contractible, homotopy equivalent to 0 complex. No, natural maps from 0 to your complex and to 0, it's homotopy equivalences, chain homotopy equivalences. This is exercise. This is the previous exercise. It's that this is true for chain complex of vector spaces of some field. And in fact, something more true, that if you have chain complex of vector spaces, then this chain complex is homotopy equivalent to homologies of this chain complex with 0 differential as chain complexes. No, there's also chain complex with 0 differential. And of course, from this you can, this follows from this, because if you have 0 homology, then this is 0 chain complex. So this is a little bit stronger statement. This is not true for free abelian groups, but this is true for vector spaces. And now your colleague say as the solution of this exercise for vector spaces. of this. Yes, and he tries to construct quasi-isomorphism. No, he now constructs. He considers that if it's vector space, then it's just direct sum of kernel of a differential and complement. And kernel is image of the previous differential and homology. It's just vector spaces. And then you have inclusion of homology in your chain complex. This map is chain map, chain homomorphism, and he claims that this chain map is quasi-isomorphic, in fact. So it's induced the isomorphism on homologies.
Yeah, now we need map in another direction. In another direction we go like this. So I'll write it here. In another direction it goes like this. So I take some element something here plus h plus something here.
No, sorry. You prove that it's not quasi-isomorphism. You prove that it's homotopy equivalence. Sorry. I said that he proves that it's quasi-isomorphism. He proved stronger result, that it's homotopy equivalence. He constructs inclusion and he needs opposite direction map. So yes, the composition are homotopy equivalent to identities. Yes, sorry. It's of course any homotopy equivalence is quasi-isomorphism, but not. Yes. No, we don't know that any quasi-isomorphism. We need to check this. Yes. So yes. He consider inclusion and consider projection. This is also a chain map, and they claim that this is the opposite homotopy equivalences. Yes.
So yeah, these are chain maps, and
No, in fact, that this is quasi-isomorphism is kind of obvious because it's homology, also okay. But in fact, this is true that it's homotopy equivalences. In fact. Okay. You have projection and inclusion. Composition of inclusion and projection, it's identity on homologies. It's obvious, okay? It's true. No, if you include and then project onto the this direct summand again, then it's identity. Yes, it's identity, and you need to check that opposite composition is homotopic to identity. Yes, opposite composition is homotopic to identity of C. Yes. It's equality. Yes. And you need the opposite. Opposite thing from C to itself is homotopic to identity of C. It's your claim. Yes.
So I just construct.
You need to construct chain homotopies. Yes.
Chain homotopies.
No, this composition is kind of projection on direct summand of H. If you consider H as the subcomplex of C, yes. Projection on H is subcomplex of C. This composition. Spin die.
This is here, and I need to project raise the.
Yes.
This one.
Yes? Oh, sorry. Identity minus. Or you have identity minus or in opposite direction. Okay. You need this. It's definition of chain homotopy. Yes,
So
right?
we need to prove this.
We need to construct such maps such that this equality holds. Yes.
And, I define the set as so I have D or something here. I forgot to say something. Plus something here, and I need to go in this direction. So here I put zeros in these places, and in the last place, for the last place I need to return here because I forgot to mention something. So
Here I don't understand what you mean. B plus star, it's some element.
yes.
This element goes to what?
For these elements, just don't enter my formula.
Okay.
Using element B.
Okay, and the image is the what?
Yes, I'll say it in a second. I forgot to mention something. So, for this, I I claim that. I claim that using these decompositions defines for me a map from not here, but so if I assume this, okay, maybe I'll write it. So this goes minus 1 is the differential, yes? And
yes, and the differential is 0 on this part, and isomorphism from this part to b and minus 1. Yes.
Yes. And if I restrict the differential,
Yeah, this is isomorphism. Yes.
so b and minus 1. This is obvious just because everything goes.
And yes, and this is isomorphism.
Yes, of vector space.
Because by definition of this.
Yes, because everything else goes to the 0.
Yes.
And here, so hence it is isomorphism, it has its inverse.
Yes.
It's inverse. And here I use this inverse. Here I go from Bn to and then
No, in your notation, I think it's IH n plus 1. Yes. Because this is n minus 1, and here n and n plus 1. Ah, okay.
Yeah, right.
Okay,
Yes,
something like this.
Yes, so we need just
No, check this equality.
yes, just by so the remaining proof is by direct check. So from one side we can consider yes, so consider this, and on the element so b plus h plus
Element of this direct sum. Yes.
by definition of projection this is I of h, and this is
It's 0 h 0. Yes. It's h.
this is this means that identity minus this
It's b plus a. Yes. It's two other sums.
on this x.
No, b plus a. Yes.
Yes, minus b plus. And from the other side, I need to consider okay, and this is
Okay, a set of this thing is by definition h of something. Yes. No, it's inverse of dn in fact. Yes, it's kind of yes.
plus 1
Plus
here is minus 1 of so here this is basically I mean it just everything else goes to 0 because just by definition.
yes.
Yes, and this is b because this is inverse.
Yes.
And this will be the definition h. Oh, I have some notation. I think I forgot, but we will see. Not the other.
No, it's kind of a. Yes. No, of course, it's kind of is a composition of these isomorphisms in the opposite direction. Yes. If you have HD, it's identity on B, it's B, and if you have GH, it's A. No, kind of this. No, what?
No, wait.
No, what? Yes, right here. One moment.
Yeah, here was the mistake.
No, it's no. It's
This must be L. This must be L.
yeah. It's X, and the dn of X is equal to dn of
Yes, and here
Yeah.
it will be
Whoa. Maybe it's more understandable. Cn of this thing, by definition, it's hn of b, hn plus 1 of b, okay. And then dn plus 1. And this is как-то взаимообратные, invertible to each together isomorphisms, okay? By definition, H is inverse isomorphism for dn restricted to ln. Dn restricted to ln is isomorphism from this part. No, this complement is part which...
Hn is isomorphic?
Yes, Hn is isomorphism invertible to, inverse to restriction of differential on ln. Ln is complement in your chain complex which goes isomorphically to the image.
Okay.
And so you have inverse isomorphism from the image to this complement. This complement is image. It's image. Yes, and in the opposite direction also. In the opposite direction you have identity on Bn. Yes. It's identity on L, and this is identity on B, because it's inverse homomorphism. So it's B plus L, and this is exactly what we need. Okay. Okay. This doesn't work for abelian groups, because in abelian groups, this you cannot say that homologies is a direct summand of free abelian group, because it's maybe not free. Homologies can have some torsion maybe. Okay, but this is true. No, you have easy corollary from this. If because your chain complex is homotopy equivalent to homologies, so if homologies is 0, then it's contractible. It's homotopy equivalent to 0. This in general does not true for abelian groups, but of free abelian groups. But this is true that if homologies is 0, then chain complex is contractible for chain complex of free abelian group. This is true, and this is a new exercise. Okay. Okay. Only for 0 is true, not for any homologies, but for 0.
Yes.
But maybe for 0 you have no torsion, so in fact you have direct decomposition of direct summands. It's true for free homologies, in fact, of course. Okay.
Yes, this was Lemma, and we need to just apply it for the case of vector space.
But you say that it's obvious.
Okay, so
No, it's going to be equivalent to homologies, and if homology is 0, then it's going to be equivalent to 0. Yes.
yes, but you at once you said that you need to prove. So this is obvious, but you said that you need to check that if it is contractible, that it is assigned.
So this is no, the opposite direction. We already know that any contractible is of course because homotopy equivalents induce isomorphism on homologies. So if two chain complex homotopy equivalent, they have isomorphic homologies. So if your chain complex is contractible, homotopy equivalence to 0, then their homologies is isomorphic to homology of 0. It's 0. Okay, this we already know this. Its new part is from acyclic. It's not always true. Okay, thank you. One fun thing here that, for example, no, not for free abelian group, but if we consider chain complex of projective modules, then it's not always true, but it's true that if you consider chain complex of projective modules, which is bounded below, which ends by zeros from some place, okay? It may be unbounded from the top, but it's bounded from the bottom, okay? From below, okay? It ends by zeros. And they all are projectives. Then it's true that if it's acyclic, then in fact this chain complex is contractible. It's homotopy equivalence to 0. Why?
Because this is projective resolution.
Yes.
0,
Yes. It's projective resolution of 0 module, exact, and ends by 0. So it's projective resolution of 0, and we know that projective resolutions are unique up to homotopy equivalence. And so, and we have 0 projective resolution of 0. So this projective resolution of 0 is projective resolution of 0. And we have 0 projective resolution of 0, and we know that any two projective resolutions of the same module are homotopy equivalent. So, okay. And here, no, it's important that it's because you consider chain complex of free modules of some ring, which is not contractible but acyclic. So it's important that it's bounded below. Okay, but what about more general fact? Is it true that No. Of course, it's not true that chain complex is gamotopy equivalent to homologies, but maybe it's true that.
What did you say about the two projective resolution of the same modulus? They are?
Yeah, they are gamotopy equivalent. Yes, because we have proved that the previous time, yes, the last time. If we have two projective resolution of the same module, because we know in fact that if you have projective resolution of two modules, then any map of modules, they exist extension of this map as a chain map. And this extension is unique up to homotopy. If you have two extensions, then you have homotopy equivalence between them. We checked that previous time. At the very beginning of the lecture, maybe yes. But from this, you obtain this fact. If you have the same module, you have, for example, identity, and you have two resolutions. Then you have extension, one extension, and you can consider another direction. You have another extension, yes? Okay? You have two extensions of this identity and this identity, okay? And if you consider composition, for example, here, this is extension of identity of M itself, but and for one resolution. But if you have one resolution, the extension of identity is, for example, identity. And so you have two extension of identity, and then they are gamotopic. So this composition is gamotopic to identity. And here is also. So this extension, in fact, are gamotopic equivalents. Opposite inverse gamotopic equivalences. Something like this. So in fact, yes, we know that. Okay, some more general is true. For example, if you have chain complex of projective and bounded below, then and for example, if you have two of such complexes of the same manner, then if you have chain map between them, if this map is gamotopic equivalence, then it's quasi-isomorphic. But no, true and inverse is also true for in this situation. Then this map is gamotopic equivalence if and only if it's quasi-isomorphic. So it's isomorphism on homologies. No, this direction is always true. This direction not always true, but it's true for bounded below projective chain complexes. Okay? Now from this it's generalization. Yes, if you have Q is 0, then we have, if it's acyclic, then map to 0, it's quasi-isomorphism, and then this statement says you that it's a homotopy equivalence. Why it's true? No, it's kind of exercise, but of course I have some kind of hint of this exercise. It's exercise, and as we already seen again from this the counterexample of Z4 differential of 2, this is not true for chain complex dot bounded below. It's important. But why it's true? Because we have construction of the cone of morphism. Yes. If we have any morphism of two chain complexes, then I can define cone of this morphism. Cone. It's some other chain complex. Definition. Cone f in ith dimension is just direct sum of c I minus 1 plus ui. And differential of cone from c I minus 1 plus ui to c I minus 2 ui minus 1 with the following formula. Cu goes to minus dc is differential of c, and differential of u plus f of c. No, the first exercise to check that this is differential. This is chain complex. Okay.
How is it? Is it somehow related to the coordinates of Lemma topology?
Very directly. Okay. No, if you consider, for example, two CW complexes, cell spaces, yes, and cell map, then cell cell chain complex of the cone of map is this chain complex. It's generated by cells of the same thing. You can check this. If you know topology, it's the same. It goes from topology, of course. It's the same thing. Okay, but now it's algebraic. I don't know, algebraic core of this definition. Okay, exercise that this is easy exercise that this is differential, so its square is 0, so it's chain complex. Okay, another thing that we have short exit sequence of chain complexes. We have natural inclusion of U to cone. Because UI to direct sum. And you can check that this inclusion is chain map. It respects differentials. You can see this from this formula. Restriction of this differential to U0 is just differential of U0. So it's the same thing as differential on U. So this map is chain map. If not obvious, then you can check this. And what the quotient of this modulo U? It's kind of C, but shifted by 1. Algebraists sometimes denote shifts by, in other manner, but I will denote shifts by in topological manner by a suspension. It's shift suspension of C. What's suspension? Suspension of C or any chain complex? It has I dimensions I minus 1, and differential, it's minus differential.
Okay. Is it somehow related to suspension topology?
In direct manner, all this notation, it's topological one. Yes, topological ones. It's the same thing. Yes, it's true. And so you can check that this is short exit sequence that exists. And if you consider the corresponding long homological exit sequence, long exit sequence in homologies, what you obtain? You obtain homologies of U goes to homologies of cone, goes to ith homologies of C, of suspension of C, of shifted C. It's the same thing as I minus 1. It's ith homology of suspension, the same thing as I minus 1 homology of C, and then boundary map goes to I minus 1 homologies of U, and you can check that for the particular definition of boundary map, this composition is induced by F. It's a map induced by F itself. So for any map of chain complex, you can include the induced map and homology to the long exit sequence with cones on two sides. Then it goes to cone and etc. So in fact, you induce homologies from C to U and then cones and etc. So for example, we have that F is quasi-isomorphism if and only if cone is acyclic. It's a direct corollary from this long exit sequence. Cone is acyclic. Because if you have long exit sequence, then one map is isomorphism if and only if they have zeros from two sides. Okay? And it's obvious. And one maybe not very obvious exercise is the first exercise which I will denote by star. That in fact it's true that F is homotopy equivalence if and only if what? What's the analog for acyclicity and quasi-acyclicity? Acyclicity is about homologies, and now it's about homotopy type of itself. When cone is contractible, if you think a little bit, maybe you can construct. In one direction it's a little bit more easier. In other direction you need some thoughts to construct homotopy inverse from contractibility of cone. But this is true. And from this general fact we obtain what I said before. If I have map between bounded below projective chain complexes, I can consider its cone. its cone is direct sums, so it's also projective and bounded below. And if this map is quasi-isomorphism, then cone is acyclic. Because it's projective and bound below, it's contractible, and so this gammatic equivalence. Okay. So if f is quasi-isomorphism, then cone is acyclic, and then because it's projective and bounded below, okay, it's contractible, and then this exercise with star, then f is gammatic equivalence. So from this general fact, we always can reduce questions about maps to questions about some chain complexes. But this reduction is not very obvious, but it's true. Okay. So what I wanted to say, that the map between two projective and bounded below map is gammatic equivalence if and only if it's quasi-isomorphism. In general, we only have direction that if it's gammatic equivalence, of course, it's quasi-isomorphism. But opposite very often it's not true, but it's true for some very good chain complexes. For example, projectives and bounded below, it's important. Okay. Also, you have cylinder of map, and maybe in some exercises on exam I will give you some exercise about cylinder. But if you consider this, for cylinder, it's some easy something like the cylinder is chain complex, and you have some other short extra sequence. It's not very easy. It's not very hard. Only not obvious part here is this exercise. Is this with star? Okay. Now let's return to the homological algebra. Why Tor 0 is tensor product, and why X0 is Hom, and why X0 is Hom. They are more or less have similar proof, so maybe let's prove tensor product. In fact, it's more or less from definition. Yes, it's not very hard. Maybe if you have more time, you solved it. Maybe because it's more or less.
I solved only for Ext, but I think.
Yes, okay. Let's say
but
answer for Ext, of course. Please formulate it.
Yes. Yes. Okay. So E is projective. If and only if E
From P to
left. F is
in fact, if you formulate it in this, and then okay, yes, okay. For any yes. And this is equivalent to say that the first X is 0, yes? Or not?
Yeah, I read about this, but I haven't think about
Okay,
it.
okay.
We can think about it.
Okay. Let's start from this formulation.
So in one direction it is obvious in this. This is obvious why. Because what's the property for being projective? To send short
Hom sends short X sequence to short X sequence.
sequences to short exact sequences. Yes.
But in general, we have long X sequence. And yes, if you have short X sequence of modules, yes.
If I consider short exact sequence of modules.
Apply Hom from P.
No, we can
Write down the exact sequence, long X sequence maybe.
I want to write projective resolution.
It's true. We already know that we have long X sequence of Ext and
yes.
Because we constructed at this manner the last time. Yes.
This is what I need.
Yes, we have this thing. We have a short X sequence of resolutions, and so we have long X sequence of homologies of resolutions, and so on.
This means that 0 goes to this is long exact induced long exact exact sequence co-homology of this complex. Yes, if I
Yes, we have from P to these resolutions and so on.
let's apply this.
This short exact sequence is splitting, so Hom on resolutions is also exact, and so we obtain short exact sequence of chain complexes of Hom from P to resolutions. And then applied to homologies, we yes, apply homologies, we obtain long sequence of homologies. And homologies by definition is Ext. Yes. And then next one.
Yes. This is 0.
This is by definition,
We know
okay.
this. This is Hom. So this is in this
Wait, stop. It's our set, we don't know this.
no, we know this. I prove it.
Ah, from right to the left, okay, okay.
So this is Hom. And this is long, okay, and this is long, it's short exact sequence. Hence,
If we have then it's 0, then
yeah.
and you can you can notice that here you only use the Ext1 as 0, yes?
Yes. Yes, yes.
So if we have that Ext1 is 0 and Ext0 is Hom, then it's projective, okay.
So this direction is obvious, and another it is like not obvious for me at least. Consider the projective resolution for n, 0, etc. And this, so apply Hom, find what I get. So this is how I denoted minus 1. And so 0. Like this. This is easy to start and so on. So now we need to. So we know that the image of dn minus 1 lies in the kernel of. It is always true.
No, because yes, if composition was 0, then
Yeah.
after applying Hom from P, composition is also 0.
So this is obvious. We need to prove to check another direction.
Now here we use definition of Ext is the homology from another direction. Yes, you have from injective resolution of n. Yes,
Yes.
just like this.
And
Sorry, but here you need injective resolution. Yes, because if you apply.
oh, of
Yeah.
course, you are right. You are right. I'm stupid. Okay, let it be P. Yeah, okay, another direction. Injective resolution. But it doesn't change anything.
No, yes. No, it's if we don't know yet that the definition does not depend on the definition of the from injective or projective resolution. Okay, we will check this from this place.
Yeah.
Okay, we need to check. You need to check the exactness of this
Yes.
chain complex. The homology to 0 because homology are X by definition. Okay.
I need to prove another direction. Take psi from the kernel. And then, by definition, this means that psi is psi 0. Yes. This means that image of psi lies in the kernel of EM. Yes. And the kernel of EM is the image of n-1. Yes. And now I can look at this diagram.
Yes, yes, yes.
Okay, have some place here.
With the image.
Yes, look here. it's not the image.
And we have psi.
Yes. The value of psi here.
No, from phi. From P.
From I?
From P. We have maps from P. Always. Because home from P. Psi is from home from P to I.
Yeah, you're
Yeah.
right. You're right. Of course.
And then you have
Yes.
lift because P is projective.
Yes, this is true because.
Yes, it's true because it
It's
takes
like-
values in image. Yes.
Yes, this is.
And now you have lift to and this means that there exists some phi.
Yes,
Yes, and this means that psi is in the image of it's composition of dn minus phi. Yes, and this image. Okay.
Okay.
No, so this exact sequence and so homological zero. Okay.
Yes, but this is not all.
Zero maybe yes only for yes.
From this construction, we also can see why.
Yeah, this works for n more than zero.
No. This works for everything. But to say about,
Yes, sorry.
to say about homology, so you will see.
No, this does not work for zero because in zero is homology that x0 is home.
Yes. I mean.
No, yes. No, you just have no I n minus one for zero. Yes.
Yes, it works, but indeed it works for every n. But for in this particular, but for to calculate homology of the Ext.
Yes, you're right.
Yes,
Sorry.
it's roll out the-
Yes, it works if I minus one is n. Yes, okay, you're right. Yes.
It always works. So I will just write this. So this means that image of m minus one equals to the kernel. Yes, start. So first of all, this means that Ext of Pn is 0. But so and now how to say that this is only because like we erase only the first term, and when we don't erase the first term, we have another equality. So for m equals 0, we have x star 0 Pn. So by definition, this is kernel of P0. Yes. I just understood that this is Polarian factor, and it is better to write star here. But okay, never mind. Yes, and here I use this equality.
It's the image, yes. Image of
So
the
because
I
this
one. Yes, yes.
for every, this holds for every n. And here is dn minus 1 for n. Minus 1. And then
But we know that the home from something is exit from the left, so it's if we have inclusion n to I0, then the image on home is the home of integers.
d minus 1 is injection.
Injection is
And hence, this is injection.
yes.
Also.
Because home from something from something it's always results in the ejections. Yes.
Yes.
It's not a question that P is projected. Yes. No, so it's home. It's isomorphic to home from M. Yes. No, okay. What about arbitrary M? It's for projective one.
Yes, for arbitrary n, I thought that for arbitrary n it is obvious from this construction. Let me see.
No, you're right. Yes, I just wanted to check this zero part of your argument and obtain that it's home. Right. No, let me check this, okay? Let me show this. Yes, it's the same thing because let me give some remarks. First of all.
You have already proved that the first one, right? You have shown that the x is equal to home when n equals 0, right? So
What?
no,
Yes.
but you started from here. You already showed that n is like different than 0.
Yeah. This is for n greater than 0. This, you see?
Yes, I see, exactly. equals
This is
0.
n
And
equals to
yeah,
0.
yeah, yeah. I'm saying that for n equals to 0, you have already done with it, showed it.
No. This is we have this because
No, by definition, X
Yes,
is
because-
it's homologies of chain complex obtained not from this chain complex, by from forgetting this part. If you don't forget this part, then it's exact. Yes, it's true.
look here.
Yeah.
We how we move from this complex to this. So first of all, we need to use Hom factor on this, and if we just directly use Hom factor, we will obtain Pn. P.
And he proved that this chain complex is exact.
Yes.
But if you need to, no, but here you have no n. If you need to forget this to calculate X by definition. And if you forget, you obtain zero homologies.
Yes, yes,
Yeah,
yes.
we just for X we just throw this away. But this chain complex is indeed
Exact.
yes.
Okay.
So we have this.
First of all, okay, let me get. First of all, we prove important property. If you have some functor, no, for example, here is Hom from P. If it
Maybe
no, one second, okay. Preserves short exact sequences, then in fact it preserves any exact sequence, and in fact it preserves homologies. It preserves homologies. No, okay, it preserves homologies. Or any exact sequences. No, it's a particular case. Yes? If something preserves short exact sequences, then in fact it preserves all exact sequences, and more generally it preserves homologies. No, we don't need here, it's kind of exercise. But you, in fact, something like check this thing. No, you check that applying Hom preserves exactness of this resolution. In fact, no, it's kind of this direct calculation. No, for me it's kind of, you can split any exact sequence on this, as I have said before, short exact sequences. Something like you have kernel to C to image, and this image is the kernel of the next one. And if you preserve this short exact sequence, then you preserve exactness in general. But no, you can check this directly, as you show us. If you have exact sequence, for example, then you can split this exact sequence on these short exact sequences. And this is kernel of next. It's something like I, D, I don't know, D, I, it's image of Di. And this is kernel of Di minus 1. And from preservedness of, I don't know, preservity, как сказать, if your Hom preserves these things, then it preserves all exact sequences by from gluing them together. It's kind of exercise, but you can check this is not very hard, and no, this is direct calculation. No, the same thing. For example, if you consider Hom 2 injective, then always it preserves short exact sequence, then it preserves all exact sequence. For general, if it's not exact, if you have homologies, then in fact you have two short exact sequences. You have this exact sequence, and you have also image is not equal to kernel, but you have that image goes to kernel of the next one, and the quotient is homology. And again, if you preserve this short exact sequence, this short exact sequence, then you can glue them together to any chain complex and obtain that your functor preserves homologies. It's important thing. So if something preserves short exact sequence, in fact it preserves all exactness and all homologies. It's true. It's because any chain complex can be split to some short exact sequences. Okay? No, you can check this exercise. You checked here directly that if P is projective, then it preserves exactness. Here you do not use that it's injective resolution. You only use exactness. Okay, it's first one. The second one is that, for example, what in fact I don't know why you didn't do this, because no, you use definition of Ext by injective resolutions from the right. But what if you use definition by projective resolution from the left? Then no, if Ext of Mn, if you say that it's homologies, oh sorry, no, it's co-homologies from Hom from projective resolution to N, then if M is projective itself, if P is projective itself, then it has projective resolution of 0 length. And so all higher X are 0. Okay?
Yes.
So yes, if P is projective, then this resolution is of 0, no, of minimal resolution. And so all higher cohomologies are 0. Okay? It's 0 for I greater than 0. No, you also need to check that. No, for 0, it's by definition it's Hom. Yes, it's identity. Okay, but for example, no, yes, and in general, no, yes, and
Can I say
yes?
about Hom?
Yes, and now okay, let you say about Hom in general. Why X0 is always Hom? Yes.
I think I have ideas.
No, this we can check directly, more or less. Yes.
No, maybe I'm not correct. I'll just return this diagram. This image, if I remember correctly, this is so. This is M for arbitrary, and we know that there exists projection from the projective. So this is psi. So we have this. So we have this. Okay.
Why?
So this is.
No, we have why we have map from M.
This is phi, and I don't know because.
No, if it was true, then you check that it's true for any projection, then you check that any M is projective. It's not true.
You are right. Okay, maybe this is okay. I'm just sleeping.
Let me formulate what we have proved so far. We checked this thing. In fact, okay, let me check directly that Hom is Ext is Hom. It does not depend on something. Or maybe okay, let me check. Ext N is Hom. Now, what you more like? Projective resolution of M or injective resolution of N? We can prove this from each one. Now, what you want? Projective of M or?
Let's be projective.
Okay. We have projective resolution. It's beginning of projective resolution, and we have N. Yes, we apply Hom to this. So we have Hom. Okay, let me consider this projective resolution, and we have, in fact, a short X sequence. We consider projection, and we have kernel. And P1 subjects onto the kernel, okay? You need to consider kernel, or quotient here, co-kernel. No, I consider projective resolution. If I have the first one, 0, 1, then it has kernel, and P1 subjects onto the kernel.
Yes.
Okay, then I know that Hom is left exact. Yes, I have Hom to N, then I have K N. Just 1 second. K N in opposite direction. Yes, M N. yes, includes to Hom. Yes, yes. N goes to Hom K N. So this Hom is isomorphic to kernel of this map, yes? Of this induced map. If it's, I don't know, F, then it's F star, then this is kernel of F star, yes? We know this, that's exit from the left. Okay?
So what's good? You just
I apply Hom, I know that Hom is exit from one side, it's from the left. I don't know that it's not surjective in general, but it's exit from the left, so this Hom is just kernel of this induced map, okay? And maybe I have surjection here. And again, but again, surjections goes to injections if Hom. So here I have injection to Hom P1. So kernel of this map is kernel of this map. And it's what you want. Because zeros homology is kernel of this map. So we obtain this Hom n is kernel of this map. It's equal to kernel, I don't know, this differential, kernel of differential one. And this is by definition, no, maybe it's kernel, it's 0, I think it's 0, yeah. It's by definition X0. Okay? It's because this map is injective. It's because this map is surjective and left exactness sends surjective maps to injective maps. Hom to something sends surjectives to injectives. And so on for Ext to injectives and Tor, so on for Tor. Also the same thing for Tor.
once again, why is it kernel F star?
Because I know that this sequence is exact. This sequence is exact. I don't know that this sequence is exact, but I know that image of this map is injective. It's kernel of this map. It's left exactness of Hom. Yes. It's because it's injective and the kernel is the image. It's exactness in this place and in this place. Yes.
Yeah,
And then I have also injection here.
And
So then kernel of this map is the same thing as kernel of the composition because this is injection. Then this is this map and this is exactly D0 star composition. It's from P1 to P0.
zero star and the kernel of the zero star.
It's by definition it's X0. Yes. Okay. So now we check that this is always true, and now you can check. You checked that if P is projective. What now? If P is projective, then Ext, all higher Ext for any M is 0, then Ext1 is 0, and you check that Ext only 1, 0, then you check that this is projective. So we check that all the things are equivalent, okay? This is because in general, if Hom from something is exact, then it preserves homologies and preserves exit sequences, preserves resolutions, and so, okay. Or because you have short resolutions for P. It's these two proofs that they are all good. For example, you also have that P is a direct summand of free model. You can check this for free model and then say that for free summands it also preserves zeros. Because for Ext of direct sum is direct sum of X, and so if it's 0, then each direct summand is 0. It's also the third proof, if you want. Okay. Also, we obtain something like this for injective. So don't leave from anything to I is 0, and we have to say that first is 0. Because if first is 0, then it's injective. Injective, then Hom to I preserves exactness, and then you have, or you have a short injective resolution for I, if you want. Anyway. Okay. No, by the same, I think you explained that Tor 0 is tensor product, okay? Because you have exactness from one side. Okay. But here, yes, maybe you have checked that projective is flat. Let's start say about flat modules. It's module M is flat if tensor product with it preserve exactness, preserve such functions called exact functions, preserves short exact sequences. As I said before, it's equivalent to say that it preserves exactness in general or preserves homologies in general. It's exercises, okay. But we know that tensor product exists from the right, so also it's equivalent to say that only we need to check that if I have injection of modules, then after tensor product they also injective. It's also injection. If for any injection tensor product is also injection, then it's flat, because we know that if we construct short exact sequence, then we know that on these two places they always exact. We don't know exactness only on this place, and this is our claim. Okay. Its definition. And okay, again, from this general thing, we obtain, in fact, that if M is flat, then tensor product is exact, so it preserves exactness. So, in fact, all Tor are 0. If M is flat, then all Tor, higher Tor, are 0 for any n. And then Tor 1 is 0. And Tor 1 is 0, it's from long exact sequence show you that this is true, because here, in fact, is in general here is Tor, yes. Tor for something, some co-kernel, yes. And if it's 0, then it's 0 here. Okay? So, in fact, it's also equivalent. Here you can also check directly that if M is flat, then it preserves exactness in general. So preserve exactness of this resolution, for example. Here you cannot say that you have short projective resolution, because maybe M is not projective. Of course, if M is projective, we obtain this thing, so we obtain that it's flat. So we бесплатно получили, что that that if it's projective, then of course it's flat. But it's not true that opposite is true. It's not general. It's also not true even over abelian groups already. But no, you can say what? Okay, for Ext we apply Hom from something or to something, and we consider such modules which are.
This is because it has resolution of.
No, for example, yes, if it's projective, then it has short resolution, then it has 0 Tors, and then it's flat. Okay.
No. I'm trying to prove that the Tor 1 is 0, and this is because they have resolution 0, P 0.
Yeah. Yes. When I say short resolution, I mean resolution of minimal length, yes, or 0 length. Yes. Okay, we consider if we apply Hom from something or Hom to something. To calculate Ext, we use good modules such as exact with respect to these functors. Okay, it's meaningful. But here we to define Tor we also use projective resolution. Okay, projective is also good for Tor, for tensor product. They are flat. But what if we obtain just flat resolution? No, what if we consider M and consider resolution exact sequence by flat modules? No, we might think that it also works because these modules are good for tensor product. They're exact for tensor products. So maybe it works. Of course, it works. We will check that from spectral sequence. Even more true if you consider such modules such that all their higher Tor with only this m is 0, then this is also work. If you consider resolution by them, then for any other model k, tensor product with them give you a Tor from k to m. It's also true. We will check all these facts from spectral sequences. So in fact, if we know this, or if we define Tor from flat resolutions, of course, this is also more or less then also we have argument about short resolutions here. If it's flat, then it have short resolution, and so all higher Tor are 0. So we don't know this yet, but we will. I hope we will check this from spectral sequences. I say that we will obtain bunch of corollaries from spectral sequences. It's one of these. Okay. Okay. Now let's say something about flat modules. Okay, let me give you some example, some exercises. Sorry, exercise. No, calculate. Oh, maybe no. Let's calculate some Tor and Ext, some easy Tor and Ext. Okay, let's calculate them. Over Z. If you have abelian groups, R is Z. Then any abelian group have free resolution of length 1, because for any abelian group, you can consider surjection from free abelian group, and then its kernel is again free already. So it has a resolution of length 1. So all your Tor and Ext, you have only 0 and 1. 0 in the first Ext. It's always true over ring. It's true. Okay, it's Tor more than it's 0 and Ext 0. And this is true for such rings that any submodule of free is free. Of free is free. Now such rings sometimes called principal ideal domains. No, it's principal ideal domains. Now also you maybe something say that R has no zero divisors also, has no zero divisors. It means that if you have two elements from R, if it's multiplication 0, then one of them is 0. And any submodule of free module is free, then it's principal ideal domain. Principal ideal domain. It's equivalent to say that this property and property that in fact any submodule of R it's ideal, it's free, so it's generated by something, but in fact then it's generated by only one element, so it's principal ideal. It's about definition. Now, for example, it's true for abelian groups and for polynomials in one variable, of a field. Or Z, for example. Now, okay, let's.
This is Hilbert's theorem, no? About polynomial.
No. It's no about polynomial. No, Hilbert has some theorem. It's Hilbert basis theorem, I think. Yes, something like this. It's for me it's kind of more or less obvious, so I don't remember the name. It's not very hard. That KT is principal ideal domain. It's not very hard. Maybe it's Hilbert basis theorem, something like this. Yes. Okay, we have no higher Tor and Ext. What about first and second? No, okay. Now, for example, 0 we know that 0 is just tensor product. For example, Z something. What is it? It's A tensor Z. It's true for any ring, yes. For any model it's A itself. Okay. What about Tor 0? What if we have that R has no zero divisors? If R has no zero divisors, then I have short axis sequence. R multiplication by R. No, from the right or from the left. If it's not commutative, you can check this. R and then quotient R modular R. This is free resolution of this cyclic module. Huh?
What is this?
It's a quotient by this submodule. It's ideal. It's left ideal generated by R.
Generated by
It's all elements of this form. It's left ideal, so I can multiply by the left by something, okay? If I consider right, yes. it's left module free resolution of this cyclic module. It's cyclic module. It's the generalization of cyclic group. It have one generator image of unit. Okay, it's cyclic. So I have this resolution. So if I, for example, let's calculate in this situation Ext and Hom from some to something. For example, Tor. If I apply tensor product with M, then I obtain M multiplication by R. It's left module, so I consider right M module and tensor product by M from the right. And I have right multiplication by M, and 0. So Tor 0, R, yes.
So what is this?
I calculate this thing by this resolution. I have this resolution if R is not zero divisor in general. I have this resolution and I apply tensor product with M because it's R, M, and multiplication by R is just multiplication by R in right M module. The same thing. And I calculate homologies. Again, I have resolution of length 1 in this particular case. So I have only 0 and 1 Tor. What the?
R divided by R, you mean, okay,
Yes.
You use 3 different notations.
No, I think I used 2 different notations. Yes.
No, you wrote in brackets, R in brackets, for this idea generated by R.
No, it's not now.
No,
Yes. No, it's because to emphasize right or left modus. It's to emphasize this thing. I use this notation. Okay. If I have braces, it's not obvious, right? Left or right. This is left module. This is left module, left ideal. So this is right module, left module. I consider this thing. Okay. If R is not commutative, it's important. No, so I have this chain complex, and again, shortest chain complex. Its homologies are co-kernel and kernel. First homology, its homology this is kernel of multiplication by R. Is R torsion of M, and this is M modular MR. No, it's the same thing as M tensor is R modular RR. Okay. What about Ext? What about Hom to something?
Why is Tor 1 like this?
What? No, it's homologies of this chain complex. It's kernel of this map. Yes? Okay. No, it's by definition it's right R torsion. So it's such elements which M such that MR is 0.
Yeah, right.
Okay, if I apply Hom to M, it's left modulus Hom to left M module. I obtain the same thing but in opposite direction. Because Hom from R to something is again M. Hom over R from R to M is isomorphic to M again, image of unit. And so again, the same thing, but with opposite ring, with opposite arrows. M. This is also a multiplication by R, but now from the left, because it's left modulus. You can check that this is true, because if I have Hom, then I have left modulus structure. This is true. No, and again I calculate these homologies, and now this is 0 and this is first. So sorry. No, sorry. This is 0 and this is first. This is 0 and this is first in the opposite direction because it's Hom from pi 1, yes, to M. This is Hom from pi 0, from P 0. Yes. This is first, this is 0. So the same answer, but in the opposite direction. Ext 0 from R to M is the same thing as Hom from R to M. No, it's also determined by the image of unit, but image of unit must be in R torsion. So it's R torsion, left R torsion of M. No, it's kernel of this map again. And Ext1 is it's M modular, yeah, because it's left module. And we see that in general, this is just abelian groups. If R is not commutative, this is not module, because this is not left submodule. It's just abelian subgroup. Because if I have elements in 0, M, I cannot multiply by something from the left. I don't obtain the same form. So in general, if R is not commutative, it's just abelian groups. If R is commutative, these are modules. If R is not commutative, this is already just abelian groups. This is already just abelian groups. It's isomorphism. What this is? Isomorphism of abelian groups. It's not R module. No. Okay. No. Sorry. This is R module in fact, because this is RB module. We have right multiplication and left multiplication. This is R module. So, but this is just abelian groups. Homologies is just abelian groups. Because this is not map of R modules in general. This is also not map of right R modules. It's just homomorphism of abelian groups. Okay. Okay, let's finish here and then we continue on lecture.